Okay, so just kind of recapping, what does exothermic look like? Exothermic has a higher potential energy to start with, lower potential energy to end with. And remember what that's showing is stability. Higher potential energy is less stable, therefore weaker overall bonds. Lower potential energy is more stable, therefore stronger bonds. So on average, the bonds of the reactants are weaker than the bonds of the product. Also remember that reactants, or for a reaction to occur, energy does have to be put in, and that is to break the bonds, okay? And then energy is released when bonds form, okay? And it's this combination, the energy going in to break the bonds compared to the energy released when bonds are formed, that gives us this endothermic or exothermic property, okay? So in this case, less energy went in to break the bond than energy that was used to release, or energy that was released when the bonds formed. Therefore, energy was released overall, or again, a net energy release, and therefore exothermic. Let's look at endothermic. Okay, endothermic is a little bit different. Our products end up at a lower potential energy, our reactants end up at a lower potential energy, and our products end up at a higher potential energy. Therefore, our reactants are stronger, are more stable, okay, and our products are weaker, are less stable in comparison. And again, that is an on average. So again, energy has to go in to break these bonds, and this is kind of what this is right here. And then energy is released when the bonds form. Okay, but notice what happens. The energy that goes in to break the bonds is much higher than the energy that is released when the bonds form. So what do we end up with? We end up with an increase in energy overall versus a decrease in energy, therefore a positive delta H. Energy has to go into the system to allow it to occur, and therefore endothermic. So again, if you kind of want that visualization of the bond curve, the bond potential energy curve, we would have our products being much lower and our reactants being much higher. So this energy has to go in to break the bonds. This energy, and actually I drew those arrows backwards. Hold on, give me a second. This is the amount of energy that goes in to break the bonds. This is the amount of energy that goes out when the bonds form. So notice much more energy goes in, a lot less energy goes out. Therefore, again, we end up with this positive delta H, or more energy being required than what is released. So that tells us that the bonds of the products are weaker versus the bonds of the reactants. Okay? All right. That takes care of bond energy. Let's look at a multiple choice problem for one of the more recent tests. What I want you to do, take a second, read the problem. Okay, and you do have a couple other answer choices down here. You have 4 answer choices altogether, but I want you to kind of ignore the answer choices to begin with. I want you to look at the problem and see what you need to do and begin solving it. Okay, and then we'll come back and actually look at the answers momentarily. Okay, so the first thing we need to do is actually understand what they're looking for. We're looking to calculate the delta H. And up to this point in time, we've talked about 2 ways to calculate delta H, which our first one is MC delta T, our Q equals MC delta T MCAT problem, are using bond energy, okay? And if you look at what we're given, we're not given anything dealing with calorimetry or MCAT, we're given bond energy. So that's the method we're going to use to solve this. And remember, the bond energy is solved by taking the sum of the reactant bonds and subtracting it from the sum of the products. Remember, that equation is not on your formula sheet. You have to remember that order. And again, I always remember that order, knowing that my reactants are going to be positive and my products are going to be negative, because energy goes in to our products, meaning it's required, or sorry, energy goes into our reactants, and therefore it is required, and positive energy is released with our products and therefore negative, okay? That may or may not help you. See if you can find a way to help you remember, okay? So first thing we want to do is use our bond energy is draw the Lewis dot structure. So hydrogen is single bonded. Chlorine is also single bonded, with each of these having 6 lone pairs around it, 3 sets of lone pairs. And then HCl is also single bonded. Okay, so from here, we want to add our reactants together, okay, and it is already nice and balanced for us. So we end up with hydrogen being 430 plus chlorine being 240. Okay, and that is the sum of our reactants minus the sum of our products will be 2 times 430. Now, Something to remember here is you do not get a calculator. I'm going to continue to stress that to you as much as physically possible. You do not get a calculator. You have to be able to do this math in your head to some extent or another, okay? So find ways to help yourself out. One of the ways I'm going to help myself out is I notice I'm adding 430 over here, subtracting two 430s, or one if I want to think about it that way, so I'm going to get rid of one of these. So I'm left with 240 minus 430, if that math makes any sense. If it doesn't, that's okay. You can do it in your head, add it, subtract it, either way. I just am simplifying it, recognizing that on the addition side over here, I have one 430. On the subtraction side over here, I have two 430, so I'm canceling one 430 off on both sides. So I'm left with 240 minus 430. Okay, now the math is pretty straightforward. 240 minus 430 is going to give us a total, okay, of negative 190. Okay, so now let's look at our answer choices. First thing we have to look at is they are giving us these wonderful little bond energy curves that we just looked at, our reaction curves that we just looked at. And we want to look at these and determine, okay, what are we looking at in terms of reaction, exothermic or endothermic? So we have a negative value, which means our delta H is negative. And what does that mean? It means it's exothermic. So the next thing we want to look at is these curves and get rid of the ones that are not exothermic. So remember, exothermic is where the reactants start higher, products start lower. So we can get rid of C, and we can get rid of D, where the reactants start lower and products end higher. So we're looking at either A or B. Now the next thing is the amount of energy that's lost needs to equate back to the energy we just calculated. Well, is that 240 or 190? It's 190. So answer is A. Okay, so that takes care of bond energy and the types of calculations we can see with bond energy. Let's continue talking a little bit more about enthalpy, and that's going to lead us into our next form of calculating enthalpy. So we talked about calculating enthalpy through Q equals MC delta T, where Q and delta H, enthalpy, are equal to each other due to the fact that there's no pressure changes, no work is being done. And we've talked about how to calculate delta H using bond energy. Let's talk about delta H a little bit further and see where we end up. Okay? So characteristics of enthalpy, what we need to recognize about enthalpy. First off, it is an extensive property, which basically means if I change the amount of stuff, I'm going to change the value of delta H, which is why we always refer back to molar enthalpy, because it's a standardized value per 1 mole. That never changes, but if I change the amount of moles, I'm going to change my delta H value overall. But molar enthalpy, the value of molar enthalpy, will stay constant. It's just how many moles we are reacting that will change. Okay, so with that being said, that also means we can play with the reactions a little bit. So if I take a reaction, okay, let's say I'm looking at this guy right here, which is our nitrogen plus oxygen forming our NO2, okay, and that's going to give us a positive 68 kilojoules. Let's say I flip the reaction. Instead of nitrogen plus oxygen, I have nitrogen dioxide, NO2, breaking down to form nitrogen and oxygen. So I've reversed the reaction. Well, if this reaction is endothermic, positive delta H, guess what the reverse is? It's exothermic. It is a negative 68. Notice both these values are exactly the same, but it's a sign that's different. And it's because these reactions are exactly the same, but they're reversed of each other. So delta H can be reversed if we change the reaction or flip the reaction. So think about it. If we go back and talk about these curves, if the reaction going this direction is endothermic, if we flip it, C would end up higher, AB would end up lower, but the amount of energy lost would be exactly the same. So we would go from A plus B going to C going to A plus B. So the value would be the same, but we would go from an endothermic reaction to an exothermic reaction. Okay. All right, the next thing is what we just talked about, is the fact that delta H is proportional to the amount of stuff that's reacting. It's an extensive property, which means if we look at the reaction we have up here, actually we look at the first reaction we have up here, which is a positive endothermic 68, we have nitrogen plus 2 oxygens forming 2 nitrogen dioxides. Well, if we double the reaction, 2 nitrogens plus 4 oxygens forming 4 nitrogen dioxides, look what it does to our delta H value. It doubles it. What if we halved it? A half nitrogen molecule plus 1 oxygen forming 1 nitrogen dioxide, it halves our delta H value. So we have this idea of the extensive physical properties. Okay? So again, enthalpy is extensive. So if we flip the reaction, we change the sign. If we change the amount of stuff, we have to also change the value of delta H accordingly. Okay, that leads into calculating delta H a different way. Now this calculation is actually called Hess's law, which we're going to look at how we calculate with Hess's law in just a minute. And yes, it is an S''S. Okay. Calculating for delta H in this way is going from products to reactants, products minus reactants, versus our bond energy equation, which I know this can be a little bit confusing and I apologize. Our bond energy is reactants minus products. Delta H using Hess's law is products minus reactants, and I'll show you why in just a minute. Okay. Actually, I have it down here. It deals with the perspective of the fact that bond energy is looking at the absolute value of our bond energies, whereas delta H is looking at the actual value, meaning it keeps the positives and negatives, so therefore we have to be cognizant of where they go. This equation is on your formula sheet, so that does make it a little bit easier. So let's look at Hess's law. Whoops, I went the wrong way. All right, Hess's law. Hess's law is looking at, first off, there's several different ways to calculate with Hess's law, so it kind of depends on what we are given. And it's taking the fact that enthalpy is a state process. So if you remember that terminology all the way back from the very, very beginning when we talked about a state process, or actually I called it a state function or state property, same idea. Okay, when we're looking at that, remember what that basically means is that it doesn't matter the steps in which it occurs so much as where it starts and where it ends. So the state of it, state being states of matter as well as the chemical formula. So again, it goes back to that climbing a hill or climbing, let's say Kennesaw Mountain. Kennesaw Mountain has two different pathways around it. It's got a stone pathway or a concrete pathway that you can walk all the way up or on the outside of it, or you can climb up the actual trail on it. They're both going to require basically the same amount of energy. One's a lot shorter, but a lot steeper. That's the trail that you climb up. Versus the concrete trail or pathway is a lot longer, but less steep. Same amount of energy because where you start and where you end is the same, regardless of what's in between. So this is kind of the same idea. So there's several different ways we can calculate Hess's law with that in mind. Okay. The first way is actually going to be looking at those series of steps, okay, and looking at those reactions, rearranging those reactions to form the original reaction. So our original reaction is this guy right here, which, yes, your book likes this reaction, so it's the one I keep using in your notes. We have nitrogen plus oxygen forming our nitrogen dioxide, which we have a delta H of 68 kilojoules. Okay, now let's say I tell you the series of steps that are involved are this down here. So think of this kind of like a mechanism, which we'll talk about with kinetics, but just kind of take that word and put it in the back of your brain. Mechanism, series of steps that occur to form the reaction. So in this case, we have nitrogen plus oxygen forming two nitrogen monoxides. It looks very similar, but it is different. And then we have two nitrogen monoxides plus oxygens forming two nitrogen dioxides. Let's say these are the two steps that occur to form this reaction. What we can do is look at these reactions, rearrange them as needed, meaning flip them, multiply, whatever we need to do, to get them to cancel out and equal this. What in the world do I mean by that? Well, think about this as kind of like a math problem. Think of the arrow as your equal sign, and think of each side being the sides of the equation. Okay? If you take these two reactions and add them together, we want everything to add up and cancel out to form this guy right here. Kind of like what we did with our electrochem, if you remember back to our redox reactions, I should say, where we had the two electrons on the same opposite sides and we canceled them out because they were the same number. This is going to work exactly the same. Now, these reactions are already set up the way we want them to, so it works out very nicely. We'll look at one where it doesn't. I have two nitrogen monoxides on both sides, so I'm going to cancel them out. I've got two oxygens on the same side, so I end up with N2 plus 2O2, leading to 2NO2. Now, guess what I do? All I have to do is add these two numbers together just the way they sit because I did not change these two reactions, and guess what we get? We get 68, which is the number that occurs for the original reaction, which is what we just got, was the original reaction from adding these two steps together. Okay? We'll come back and look at Hess's law in just a moment.